Seems like it might work. See if there's anybody on the Zoom. Oh yeah, we have somebody on the Zoom. Can you hear me?
Yeah, I can hear you.
Okay, very good. Just check the settings. Okay. Okay. All right. Hopefully, it'll give us a cleaner sound, and then when I write on the board as well, it's supposed to track and capture the board as well, which will hopefully be useful as we move further into the course, and I'm writing more on the board than just using PowerPoint. Okay. Starting. Okay, so continuing on from our last class, we'll conclude with a few comments about quantum physics. Before I start, does anybody have questions? Did everybody see that there was a homework that is due this Sunday? You all see it in your canvas? Okay. Yeah, if you have any questions, you can come talk to me after this class in the office hours or after class on Friday. Or if you need another time, just let me know. Okay. So the outline for this week, probably get through hopefully half of these today, and the remaining half in the next class. So we want to finish up the conclusions about quantum physics. I mean, whatever we discussed. We will talk about classical computers now. So we're starting the sort of computational part of this course. And for some of you, much of this might be review. We'll talk a little bit about binary logic and arithmetic, binary logic gates, universal binary logic gate sets, and then reversible logic gates and error correction in digital binary logic. And then that'll finally we'll conclude with a few general comments about Turing machines and complexity classes and the Church Turing thesis. So this is sort of an overview of many developments in classical computing that have taken, as you know, many decades of work. And our focus is going to be to just explore sort of what classical logic is and these various ways in which we can define the limits of classical computing and understand some of these gate sets, because it will turn out that there's some strong analogies with what we'll do in circuit-based quantum computing. Remember, we said there are 4 models of quantum computing, and one of them is a circuit-based quantum computing, which will have close analogies with the circuit-based classical computing. So, okay, so the first part is I'm just reminding you that the main thing we discussed last time was a single photon or single particle interference. And that is the phenomenon that Richard Feynman said was at the true central mystery of quantum mechanics. And instead of doing a double slit experiment, remember we did the I showed you like you can do double slit experiment with like electrons. You can also do double slit electrons with photons, of course, but a simpler version or a more experimentally easy to manipulate version is the interferometer, which is sketched here. I briefly talked about this one, that you send photons into this interferometer. They're split into two paths, so that's like the two slits of the Young's double slit interferometer. And then when they recombine, that results in interference. So that's allowing the waves to propagate and then recombine on the screen in the Young's double slit experiment. So you can think of each path, path 1 and path 2, like the two double slits, and then the recombination on these detectors, like looking at the interference fringes on the screen. Okay. So in the last class, I ended with an overview of a famous experiment, a famous thought experiment by Wheeler, which is called Wheeler's delayed choice experiment, where the idea of the Wheeler's delayed choice was that if a photon can either take path 1 or path 2, that's like the two slits of the electron in the electron interferometer. And then when it recombines, it can either create a wave-like interference pattern, or if we observe which path it's coming into, then it'll be like observing which slit the electron went into, which will then remove the interference fringes. Okay, so and his idea was to make the choice of whether to combine the beams or not combine the beams well after the photon had already traveled through the interferometer. So the question of which path it was taking would not be decided until well after it had already sort of somehow gone through the interferometer. So this was his idea, and it was realized experimentally. I mean, his idea was just move this beam splitter in and out based on some signal that it doesn't have enough time to propagate back to this point here and tell the photon, oh, wait a minute, I'm in here, now you have to be a wave. Or I'm not here, oh, now you better be a particle and choose only one path or the other. Okay, so this is the sort of his Gedanken experiment. And then it was realized experimentally. It was already realized in a couple of different ways, but realized, I think, almost in sort of the best way, using the single photon source from an NV center, which I've told you about before. And that's all. I'm just summarizing all that information in this. And they indeed saw this. So they saw that if they made the choice, and of course the choice was made randomly, so that even the experimenters didn't have any control of when the beam splitter goes in and out. So that, truly, there's no way that the experimenter could have somehow gone back and adjusted the interference pattern of the photon. Then they found that indeed interference will just either appear or disappear depending on whether the beam splitter has been put in or out. And that choice, as I said, happens well after, so to speak, the photon already has gone through the interferometer or gone through the beam splitters, through the two double slits. So that's the basic principle of this experiment, and it confirms the quantum mechanical predictions. And so again, we have this problem that matter behaves like particles or waves, depending on the experiment. But even more amazingly, it seems to depend on that even after, say, you make the choice whether to observe the particle or wave nature of that object. And that is what is, of course, a sort of central mystery of quantum mechanics. And one interpretation that is often used, and we'll refer to it as well. One interpretation is that the particle, the photon, for example, does not have a location, okay, until it is observed. Like until the point when it hits the detector, it has no definite location. Until then, all you can do is describe it through these waves, these probability waves, like the ones that Schrodinger incorporated or implemented in a Schrodinger wave equation. And, for example, there's the left and the right positions of an electron, or electrons going through double slits, photons going through beam splitters. And we describe these waves in a superposition when they are in these multiple different positions. Okay, and there are other properties, momentum, angular momentum, etc. All are also described in this way. And we then have to, only when we decide to observe, is when we will know the exact value of this point of this property. And of course, that's it struck a lot of people the wrong way. It meant that things didn't really have any definite reality, as you might call it, until you decided to observe them. And so that was something that Einstein never agreed with until the very end. And but it did give rise to a lot of interesting thought experiments, which have now been, many of them have been realized, and We have tested the quantum mechanical predictions very accurately. So in some sense, you can say, look, the quantum mechanical predictions are quantum mechanical predictions. We have certain, it's like a mathematical formula, right? It's like you have certain axioms, you follow them, you interpret, and then how you decide to interpret them, that's on you. That's you are projecting your view of the world onto what quantum mechanics wants to do. At least that's one way to think about, what's happening in the quantum world. But of course, this also means that we're stepping back from saying that we can actually, understand this quantum world in a more, physical fashion or intuitive fashion. And we just have to follow what quantum mechanics is. But yeah, so this is the big, sort of paradoxes and ideas that people debated. When is the particle observed? Is it when it hits the detector? What is it in the detector that magically, is it the first electron that's released when a photon hits the detector? Or does it have to be like multiple electrons have to be released? Is it not really observed until something like a voltage pulse is created? Or is it not observed till on the screen, somebody looks at the screen to see that there was an electron on the screen? When exactly is the act of observation done, right? This is the big sort of question that one has. And I would say that even now, we still have a lot of debate about this question, okay? People, are like, who has to look at it? Human, camera, people, you will hear these statements, oh, it has to be consciousness. That's what collapses the wave function. I would say that that's kind of, a little bit of one of those interpretations that I don't agree with. But it's just, some of the things that people will say when you listen to these questions and debates. Okay, and we'll try to address some of this as we get through the course. Obviously, this is not a quantum physics course, so we won't be talking a lot about these things, but I just wanted to point it out. And the last one, of course, the cat, that's the famous Schrodinger cat experiment, thought experiment, where Schrodinger said, if you have a gas of poisonous, in case somebody doesn't know this, I think everybody here probably does, but I'll repeat the experiment again, just in case you haven't heard it. So there's a box with a cat in the box and then a vial of poisonous gas. And the poisonous gas has a hammer that will break the vial, okay? So the vial will be broken and the poisonous gas will be released. And with 100% probability after that, the cat will die. But the release of the hammer is determined by the decay of a radioactive particle, a radioactive atom, one atom, for example, in this case, okay? So the idea is that if you have just one atom, a radioactive atom, you don't know when it's going to decay, right? Because as we know from quantum mechanics, it will be in a superposition of decayed and not decayed in some sense, okay? And, that was well known to them, right? They couldn't predict exactly when they would observe a detection or a click from a radioactive sample, but they could predict some Poisson statistics, for example, for the lifetime of that sample and so on. But anyway, so when you have just one atom which is decaying, or you can think of this as like one photon that's emanated by a single photon source, we never know when exactly that photon is going to come out, for example, with a single photon source. So anyway, so then the question is, what is the state of the cat? And if this experiment is true, then indeed the cat is in a superposition in some sense of atom not decaying and the cat is alive, or atom decaying and the cat is dead. Right, so that's the two states of the whole box, this closed box. And of course, the question is, can you really build a closed box like this? That's sort of the big question, right? Because the cat is a macroscopic object, and so the question is, can it really? And this kind of a state where two objects are in the superposition of properties is called an entangled state. Okay, and that's really what entanglement is about. It's like these two properties of two different objects which are now combined together in a quantum superposition. And we'll have more to say about this when we discuss quantum entanglement. This gives rise to yet another type of experiment, which is called the Wheeler's delay choice with quantum erasure. Earlier, we did a classical erasure experiment. Erasure just is the idea of like, I'm erasing the which way path information using a classical signal in that case. In that case, a classical signal is some random number decides whether to put the B splitter in or out. In this case, it's a quantum object that decides whether which way information will be observed or not. But we'll come back to this experiment later on. And this has been also done, by the way, this Wheeler's delay choice with quantum erasure. So I'll come back to this experiment when we discuss quantum entanglement. So what I should mention before we leave this topic and move on to classical computing is that this is an area of current research. Okay, we are still exploring the foundations of quantum mechanics and trying to understand this with experiments. And the kinds of experiments that we are thinking about is how big can we make a quantum superposition? Certainly, we know we can make it with photons and atoms, electrons, and so on. Can we make them bigger? Okay, and if we make them bigger, how long does a superposition last? Remember, we talked about this as the coherence time, which is how long the quantumness of the state will last. And we'll come back again to these ideas. Yes.
What's the advantage to making it?
Well, this is exactly the point that we were just discussing. How big will the superposition last? You know, can I make a kitten or a cat into a quantum superposition the way that thought experiment was made? You know, the principles of quantum mechanics don't seem to forbid it, but experimentally, can we do it? And the reason I should say that people are interested in this is there are at least two other theories of quantum mechanics. Many theories have been proposed to modify quantum mechanics. Okay, so quantum mechanics, when I talk about it, of course, we are only going to present the standard theory of quantum mechanics. But there have been many proposals to modify quantum mechanics. Everything from like people adding a little nonlinear term to the Schrodinger equation, okay, which allows for like extremely powerful quantum computers to be built if we had this little bit of nonlinearity. But it turns out such nonlinear terms violate some well-observed other principles of quantum of the world. So we know that probably those terms will not be likely to be there in the real theory, okay, the full theory, so to speak. So if, you know, for example, there are problems with quantum theory, you know, which is what Einstein claimed all along, then we should explore, you know, are there some other theories that are better than the quantum theory? And so one way to test such theories, one theory is, you know, that there is something that causes wave functions that are bigger than a certain size to collapse in the theory. So you can add in some terms that make bigger objects collapse, but don't do anything to smaller objects. Okay, why? I mean, that's a separate question. You know, first we have to explore whether, you know, such a thing can explain everything that quantum mechanics does, but now start to predict that you can't create a Schrodinger cat, for example, a real cat in a Schrodinger state, in a superposition state. And we can test these ideas by making bigger objects and seeing how long they last in this quantum superposition. And there's a parameter which is called the macroscopicity parameter. You don't have to know this. I'm just explaining this is like a current research area. Like, you know, people actually care about this right now, right? People are trying to understand this. And I should say that the quantum superposition has been achieved with objects that are bigger than just electrons and photons. Okay, so people have done them with molecules that are fairly big, that look like this. Okay, so these are not like as tiny as atoms or electrons or even photons in some sense. But photons are massless and they kind of, you know, behave naturally quantum in some way. But you can see interference patterns when they go through these fringes. And superconducting rings, for example, are billions of electrons moving around this ring, either round this way or round that way. They have created superpositions of that as well. Okay, so those are also macroscopic quantum superpositions. And neutrons was another early thing that people did with neutrons, which, okay, that's still, you know, sort of classical, quantum. And so this is just a plot of this macroscopicity parameter, which I was just talking about. And it's as you can see, it's because it's a log scale. Anything that's like, you know, up by a factor of 2 is like actually 100 times bigger or more macroscopic than the other one, right? And so you can kind of see, you know, neutrons were the first ones that people were doing with these blue dots. And then they started, these are cold neutrons. So their wave functions are sort of very large compared to, say, atoms or electrons and so on. And then you can see this steadily it has grown. You know, we have atoms here in these triangles. We have molecules. Initially, the molecule experiments were quite small, but by now, you know, they are the sort of the leading sort of experiments. And I should mention, like, you know, in my lab, we try to do things with like nanocrystals, diamond nanocrystals, and we're trying to like put them into quantum superpositions because those would be truly macroscopic objects. They're only a few nanometers, but nanometer is a gigantic size at the quantum scale, right? So these are, I'm not the, obviously our lab is not the only one. There are lots of other people trying to put superpositions of a lot of other types of spheres and levitated objects and so on. So it's a kind of a interesting area right now. It's quite unique for people to like examine these kinds of superpositions and try to achieve them. And this plot stops in 2010 because the paper I took it from is written in 2014. There's been progress since then, but I haven't gotten around to updating this plot. Okay, so I'll just leave this at the very end. Hopefully we don't get to a situation like this where we are, killing cats as we try to lay this problem to rest and solve the Schrodinger's cat issue. All right. I should mention, of course, there's at least one other interpretation of quantum mechanics that it says we don't need to involve these collapse ideas or measurement postulates and all that. We just say that the only thing that exists is the Schrodinger equation. And that's the only thing that is there. Okay. And so what happens if, for example, an atom decays? Well, what happens is that the universe branches off into two different branches. Okay, and one branch, the atom has decayed, and the particle and the cat is dead, and the other branch, the atom is not decayed, and the particle and the cat is alive. And of course, you may say, wait a minute, this leads to like billions, trillions of universes. But of course, there is a theory behind how to like understand what happens in a given universe and how you can calculate probabilities in that universe, even though, there are all these other universes. So there's no real, I would say, like sort of contradiction. It just means that you have to account for the fact that there are, in this theory, in principle, there are millions of universes, billions, trillions, multiverse or so in this situation. And so I would say for most scientists, it's like most working scientists, we don't worry about this, right? We are like day to day, I just work, man. Like, don't ask me what's actually happening, and it's just shut up and calculate theory. It's just like, this is what I think in the beginning they did as well. And, and now we know how to calculate a little better, but, it's still the same principle, basically. Okay, and whatever you want to interpret quantum mechanics as, we know that it's verified and used countless times every day in almost every device that you have around in your house, in your pocket, etc. When you go driving, you use GPS, and that's using some atomic clocks, which are also built using principles of quantum mechanics. You go in for an MRI, that's being used. Hopefully, you don't need an MRI, but if you do, at least it's there, right? So you don't have to be cut open to find out what is happening. Okay. All right, I'm going to stop there. Any questions about all this? We will, of course, return to the mathematical formalism in a week or so. We'll introduce quantum bits, but any questions about the sort of overall views and pictures of this? Yes.
We're probably going to get into it, but I have a question. It's like, how does entanglement and superposition practice? Like, how does that relate to
Quantum computing? Yeah. That's a good question. So how does entanglement work in quantum computing? Well, I mean, I would say on one sense, at least in the circuit model of quantum computation, it happens that there's entanglement during the quantum computation, and people theorize that the power of the quantum computer comes from this entanglement. And that's what we believe gives a quantum computer its power. Okay.
We don't really know exactly like how quantum computers working, but we have like this theory behind why it's working.
I mean, we understand what the quantum computer is doing, and we know that during that process there is an entangled state that's created. Do we understand exactly why the entangled state matters so much? I would say that people have various theories on that. So there's things like information capacity of like quantum channels and quantum information theory that tries to talk about like, when you have this certain kinds of, I mean, I don't want to get into the mathematical language here, but there are certain states, quantum states, that people believe is a subset of all the possible quantum states that there could be. And they believe that these are the states that help you in these quantum computers. Right. And so that's certainly something up for research question, like which states in the quantum computer are helpful for quantum computation. And if we can keep the quantum computer in those states, then maybe the computation will be proceeding faster or better, for example. And anything that takes you out of those states is bad for quantum computing. That's what is theorized. But until we build some of these things and like test these ideas, we won't really know, right? I mean, it's a theory at this point. Yeah. But great question. Thank you. All right. So now we're going to switch gears. We're going to first start with classical computers. We're going to discuss some of the classical computers and ideas. So we'll begin with the very beginning with classical analog computers, because you'll see, in some sense, quantum computing is a return to classical analog computing. Okay, and we'll have something to say about this. So by the 1950s, analog circuits were already in wide use for computation. For example, people were solving, differential equations to predict, things. As an example, the atomic bomb, modeling the explosion, modeling the way in which. But I mean, besides that, things like aerodynamics and stuff like that. This was all like really useful stuff to be able to solve those equations and predict what would happen in all those situations. And invention of things like the op-amp. If you take an electronic course, you probably cannot miss hearing about the op-amp. That makes constructing circuits for many mathematical operations just very straightforward. It's almost like plug and play. Take a bunch of different op-amp circuits, line them up, put them together, and you can basically create like, solution to differential equations, for example. But within about 20 years from then, we switched over from analog to digital, in particular, we switched over to digital binary logic. Binary meaning that we only have two states in the computer, 0 and 1. Okay. And what? And this sketch sort of illustrates this problem. So in the analog computer, right, basically what is happening is that you put in some signal, right, like input to the computer, and that input is usually, let's say it has some voltage signal that looks like this. And, within this, there might be many levels, right, that the computer can use to say, okay, at this level, I have this decision and I'm going to do this. This level, I'm going to do this, for example, as a way of thinking about the computer. But of course, we know that in real electronic circuits, there's always some amount of noise and distortion that creeps into the circuit. It's just inevitable given the way in which analog op-amp circuits, for example, are constructed due to the resistor noise, and as well as like things like op-amp saturation. This is just a standard thing with transistors in general. So as soon as you have this kind of noise and distortion, your analog computation gets affected. You might get a wrong answer after many layers of analog computation. Furthermore, so that's the reason we went to a digital signal, because you can see in a digital signal, if I denote the states of my computer, say 0 when the voltage is low, and 1 when the voltage is high inside the computer, then even if the signal gets distorted, which it does, it always does. If you look at the output of like a PC board in a computer, you will see lots of these little signals, and they'll all look like crap, okay? There'll be like lots of noise on them because there's so many digital signals all in close proximity. There's crosstalk, there's all kinds of things going on. But it doesn't matter, okay? Because we can distinguish 0 and 1 very easily, right? Even with our untrained eye, and then you can build circuits, to like distinguish them practically as well. And so some of the reasons, I just outlined them here. There's a limited dynamic range. So for example, let's say the circuit can resolve a change in 1 millivolt out of a total signal range of 0 to 10 volts. So, you have a 0 to 10 volt signal range, which is fairly normal for an op-amp circuit. And let's say you can figure out with the noise in the circuit, to be safe, I'll say that a signal of 1 millivolt means that there's a change in the voltage level. Well, that means that I only have 4 digits of precision in my computer, because I have 1 millivolt out of 100 out of 10,000 millivolts, right? So we have to keep the signal within a limited range due to these op-amps, and so that means with only 4 digits of precision, you can't like do a lot of operations beyond that 4 digits. And furthermore, if the signal must be maintained within the 10 volts, you can't just make it 100 volts suddenly, because the op-amps all will go into saturation and you can't like do any of the operations. So you have to then say, I can't really do floating point operations. So, if I have like a number that I want to represent by like, several digits of my decimal places, I'm restricted to like these 4 digits. I can't do like 10 to the 5 or 10 to the 9 or whatever it is, other types of operations. which often arise in scientific computing, right? When you're trying to like numerically calculate some path of some atom or path of some not atom, but differential equations, this often arises. Okay, so that's all I have to say about analog computing. Just keep this in mind, because when you come back to quantum computing, you'll see we have to return back to some of these bad old days. Okay, so we'll come back to that later. So digital or binary computing is less sensitive to that noise. You can easily do error correction, which we'll talk about in this class a little bit. And it's easier, of course. By now, we know how easy this is to program with algorithms. And it has unlimited dynamic range. Just add one more bit, and you've got extra factor of 2 in all the numbers that you can represent, as we'll see in a minute. And with, of course, this couldn't have been known back then when they started working with this. But by now, we know that by using CMOS technology, we can miniaturize things extremely small. We've talked about Moore's law, and it can be done at low power, so we're not burning up a lot of watts in the computation. Okay, so let's talk about Boolean logic. Boolean logic was first formulated in the rules of true-false statements in the logic, the field of logic as a mathematical or philosophical branch. The true-false logic was first formulated in 1854, this mathematics of it. And then in 1938, it was Claude Shannon, who's very famous in communications theory and information theory, who applied Boolean algebra. He was the one who realized that there is this thing called Boolean algebra. This is once again an example of something that people thought of just some person randomly invented something in math, and who knows, who cares what this is good for. But it took someone like Shannon to realize, oh, I can take this Boolean algebra and I can apply it to something very practical, which was the design at the time of like telephone switching circuits. And he figured out how to use this. And then he was able to then, from this, make some very powerful theorems about universal gate logic sets. Okay, we'll talk about that later. So that's one of the big impetus. I think there were 2 other people who are also credited with this at around the same time, who also applied Boolean algebra to this. But the one I was taught back when I was learning this was Claude Shannon. So I just put that up. Okay, so what are the main things in Boolean algebra? Well, it's very simple. We have 2 constants, 0 and 1. And variables in this algebra are represented as capital A, capital B, capital C. And then we can have lots of functions between the variables. Okay. So a variable can only take on those 2 values. It can be either 0 or 1, but it's at least undefined. And we have to see what happens for different situations. And there are different functions. The functions, for example, which are most common are AND, which is given the symbol dot. And that will be, the expression will be A dot B or just simply AB. And that will be equal to C. This is the rules of the algebra. Okay. And then there's the OR operator, which is A plus B is equal to C. And then the NOT operator, which is denoted by the bar. So A bar equal to C. Okay. So as we move into binary logic, it helps to first think about binary numbers. And so probably most of you know this, but I'm just quickly reviewing it. If you don't know it or you're confused, please don't hesitate to stop me. So in normal decimal arithmetic, which is the number system that we're all familiar with and we use most often, if you have a number like say 1, 2, 3, 4, then that represents the following number. We take the most significant digit, which is the leftmost digit. We multiply it by 10 to the 3. That's because it's 0, 1, 2, 3 is the exponent of the 10, right? So the rightmost digit is multiplied by 10 to the 0, which is 1. The next digit is 10 to the 1. 10 to the 2, 10 to the 3, and that gives us 1,234 in our decimal system. And we can also represent further floating point or decimal numbers, irrational numbers, etc., by just continuing that series. So after 10 to the 0 comes 10 to the minus 1, 10 to the minus 2, etc., etc. So now we can do the same thing with binary numbers. And so the way in which we denote the binary numbers will be, here's a binary number, a constant, with a 2 subscript, which denotes that it is in binary notation. Okay? And so then the same logic applies, or same idea applies. 1 times 10 to the 2 to the 0, 0 times 2 to the 1, 1 times 2 to the 2, 1 times 2 to the 3. Add them all together, you get 13. Okay? 13 in regular, I should really put 13 subscript 10, because that's in our decimal notation. So base 10 notation, if you like. But of course, we don't do that. We assume that everything is written in base 10 usually. After a while, of course, we'll be purely using binary numbers, and so I won't bother putting the 2 down there. It'll hopefully be clear from the context. And here, for example, we can also expand to having a decimal point, or I guess it should be really called a binary point over here. So after this point, we now multiply by 0 times 2 to the minus 1, 0 times 2 to the minus 2, etc., etc. Okay, and if you want to convert, so the way I wrote it for you was take a binary number, convert it to a decimal number. We can go the other way. So if I take the decimal number 13 and I want to convert it to a binary number, I divide by 2. Okay, so I'll get a quotient 6 and a remainder 1. Okay, then I take that 6. I again divide that by 2. I get a quotient 3 and a remainder 0. Take the 3. Again, I get a quotient 1, remainder 1. And I get, again, I take that 1 and I divide by 2. I get a quotient 0 and remainder 1. And that's when the operation stops. And then the digits that are left as the remainders, 1, 1, 0, 1, when I write it from right to left, like, gives me the binary representation. So just essentially like the inverse of the multiplication that we did to go from binary to decimal. We do the inverse division operations to go from decimal to binary. So one other common thing that you'll see when you do computer programming is the base 16 or hexadecimal numbers. There's also base 8, which is octal notation. It's not very commonly used, but it is there. But the idea is that we can represent numbers because often in binary, you end up with long strings of binary digits to represent even small numbers, okay? Well, reasonably small numbers. So that can be pretty painful to write out. So instead of writing out all the numbers, instead we go in groups of sort of 4, because if you take a group of 4 binary digits, that represents numbers from 0 up to 15, okay? You can work that out yourself. If I have 4 binary digits, that's all the numbers from 0 up to 15. So those 0 up to 15 are represented by 0, 1, 2, 3 up to 9, which are the usual decimal numbers, and then A, B, C, D, E, F, okay, which represents the numbers 10, 11, 12, 13, 14, 15, okay? And so if I take a number like this, 0, 0, 1, 0, 1, 1, 0, 1, I group them by 4s, okay, I convert each of these to a decimal number. In this case, that's the decimal number D, or in hexadecimal notation, that's the hexadecimal digit D, which is the number 13, okay? And then we have this one, 0, 0, 1, 0, that is just the number 2, so that's 2, so this is 2D to base 16, okay? And of course, we can calculate 2D to the base 16 by simply taking the 2, multiplying it by 16, plus D, which is 13, multiply those two, add those two together, you get 45. And you can then verify for yourself that the original binary number, which is written here, 0, 0, 1, 0, 1, 1, 0, 1, if I convert that using binary, I'll also get 45. Okay, easy enough to verify. Okay, so this is just another notation. It'll sometimes pop up when we're doing programming of various codes and things like that. Any questions? Eric? Are you raising your hand? Oh, okay. Sorry. Okay. Now, of course, we know that numbers don't just end with positive numbers. We also want to represent negative numbers. How do we do that in binary? Negative numbers are represented by something called the 2's complement method. There are 2 ways to think about this. The first way I'll just show you here, which is that the very first digit is treated as a negative number, okay, when it's in 2's complement notation. So is you put a -1 in front of it and then multiply it by, again, the powers of 2 that we have already talked about. So -1 times 2 to the 4 plus etc., etc. So those etc's are -16 plus 8 plus 0 plus 2 plus 0, right? So that's the number -6, okay? So this is one way of understanding the 2's complement method. The other way to think about this is to write the corresponding positive number, that is 6. I write it as the corresponding positive number, and then I make each 0 to 1 and each 1 to 0. This is called the 1's complement, because it basically flips. each bit, okay? And then I add 1 to the remaining number. And so this is called the 2's complement, okay? And that is shown here. So I write the number 6 in first in 1's complement in regular binary notation. Note that I've kept this last digit here because that's I originally started with this 5 bits. So I want to represent this as a 0 in that 5-bit string. Okay, so 0, 0, 1, 1, 0. This is the number 6. I take the 1's complement. That's flipping each of these bits is 1, 1, 0, 0, 1. And now I add 1 to it. Okay. So, I guess I forgot. Did I skip something? Because I thought I guess I didn't introduce addition. Okay. Sorry. It's on the next slide. But okay. So let me just tell you what happens when you add binary numbers. It's pretty straightforward. It's 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 should be the number 2 in binary, in decimal, which is just 1, 0 in binary. Okay, so that's the one difference, right? Because 1, 0, now I had to go an extra bit over to the left, which is what happens here. So when I add 1 to this 1, 1, 0, 0, 1, the first 1 plus 1 gives me a 0 with a carry of 1, right? So that carry is this 1 over here, and then the rest just remains the same. Nothing happens to those, right? And so you get minus 6. Which is because 1, 1, 0, 1, 0 was how we wrote the original minus 6 in 2's complement notation. Clearly, this reduces the maximum value of the numbers represented because of the 5-bit string. If they were all positive numbers, I could go from 0 up to 2 to the 5 minus 1, right? Because, for example, I have 3 bits, I'll go from 0 up to 2 to the 3 minus 1. 4, 0 up to 2 to the 4 minus 1, which was 15, like the hexadecimal numbers we just talked about. And then if I go 5, I should be able to go from 0 up to 31 in this case. But if I now use that last bit to denote the sign of the number, then of course I reduce the total value of the numbers that I can represent. So that's just one of the outcomes of this notation. Okay, you're all probably, if you've done some programming, you probably have heard about this. Okay, I already talked about addition. So I'm just showing addition of 2 numbers. Again, fairly straightforward. 0 plus 1 is 1. 1 plus 1 is 0 with the carry of 1. Again, I add 1 and 1. That gives me a 0 with a carry of 1. And then the last one gives me 1 plus 1, the 0 with a carry of 1. Subtraction becomes very easy in the 2's complement notation. That's why we use it. Okay. You simply find the 2's complement of a number and add it to the other number. Okay. So let's say I want to take 5 and subtract 3 from it. Okay. Then I write 5 in binary notation and 3 in binary notation. Right. This is the binary notation for 3. That's the binary notation for 5. So then to find 3, to subtract it, I first find its 2's complement, which of course we know the way to do that is to take the 1's complement. That is 1, 1, 0, 0 is the 1's complement of 3. Okay. And that's 0, 1, 0, 1. That's just 5. I've just carried it over, okay, to this screen over here. And then I add 1, 2. Right. Because finding the 2's complement is taking the 1's complement and adding 1. So now I just need to add all 3 of these numbers. Or I need to add 0, 1, 0, 1 to 1, 1, 0, 1. Okay. So that's 0, 1, 0, 1 to 1, 1, 0, 1. So now I calculate that. It's 1 and 1. When I add that, that's a 0. And that carries the 1. Add 1 and 1. That carries a 0. And add, and that gives you a 0 and carries the 1. And then 1 plus 1 is again a 0. And then there's a third. And there's an overflow bit, 1, which we throw in this 2's complement way of doing some subtraction. Okay. So the overflow in 2's complement is always thrown away in this way of doing subtraction. Okay. And of course, the answer is no surprise. Okay. Okay. So besides the various binary, I didn't talk about multiplication and division. We can do those as well, but I won't get into that here. This is something that will be covered if we do any other. If we need to do it, we'll talk about it, but it's really not usually needed. It can be done. It's not very difficult. Okay, so we also need a way in normal computers to encode not just numbers, but also other things like letters, text, punctuation, images, etc., into binary. Okay. And so when you want to encode at least text, which is letters and punctuations and other types of things into binary, there is a standard that evolved, which is called the American Standard Code for Information Interchange, which is ASCII, right? And this ASCII, it uses 7 bits, okay? And those 7 bits encode 128 possible states. Okay, this is all, just some information. 95 of them are printable characters. You can just look at your textbook. It has the ASCII table there, or you can just Google it. It's all there. And mostly, we never have to do that. If you write any kind of programming language, it usually can just do it for you. Okay. And the one thing you should know nowadays is, of course, to allow for other languages, things like any other types of characters, and also nowadays with emojis and so on. The standard that is now used it's called UTF-8, and that has 32 bits instead of 7 bits. So it's a bit bigger file when you save it in UTF-8 format. Okay, so that was just about like how we represent numbers and represent letters. So as you can see, anything can be represented in this binary form. And now you can ask yourself, how do we? So everything like word processing is just some bunch of arithmetic operations on these binary digits. And so how do we do these manipulations, these operations, like say addition? I'm just going to take addition as the simplest example, and we'll discuss that in a minute. But we basically want to manipulate these bits, right? And we want to manipulate these bits using something called binary logic gates. Okay. And so what the logic gate does is it takes 1 or more bits as an input and then outputs 1 or more bits. Okay, very simple. So it's essentially mathematically, it's a function that takes binary strings and maps them onto other binary strings of some other dimension in the sense of length. I could have like a 10-bit binary string and I output either a 0 or 1, just 1 bit, or I can output another 10-bit binary string, for example. So let's look at first the most obvious one, which is single-bit logic gates. Okay. So the single-bit logic gate, as the name suggests, it takes an input, which is one of the binary digits, and puts an output over there. Okay. So how many possible single-bit logic gates can there be? Saw someone raise 2. Nobody wants to speak up? What's the answer? Yes. Yes, you.
Yeah, 2.
2. Okay. So why is that?
There's a NOT gate and there's a buffer.
Oh, yes. In that sense, what you're saying is that there can be a gate. You already know about NOT gate, for example, right? But I'm saying just think about it as how many possible input states and output states can there be for this system? How many input states?
2.
2. How many output states? 2. So how many possible gates are there?
4.
4. Very good. Excellent. 2 times 2. Right? Because for each of the inputs, there are 2 possible outputs, basically. That's what I'm trying to get at. Very good. So that's what is also represented by the truth table. For every input, I can have, 2 possible outputs, right? And each of those truth tables represents a different logic. Okay. Does that make sense? So the idea of the truth table is very powerful, as we'll see, and we'll return to it in quantum as well. So as you just said, the most obvious one is the identity or buffer gate. Okay. So it's sometimes represented by this triangle symbol, but most often it's just a wire, right? Because a buffer gate is one that does nothing to the input. So the input A becomes the output A as well. Input A means A can be either 0 or 1, and the output will then be the same as A. And the truth table for that is very simple. It's the identity operator. Is 0 goes to 0, 1 goes to 1. Okay. The NOT gate, as you pointed out, will be the one that flips those 2 operations. Okay, so 0 goes to 1, 1 goes to 0, and we denote that with a triangle with a circle at the end. Okay. And the notation, as we have said before, is A goes to A bar. Okay. And then there are two other possible gates, which is think of them as like a constant gate, right? Which is if you have 0 or 1, the output is always 0, or 0 or 1, the output is always 1. So those are the four possible single bit logic gates. Now let's talk about the 2-bit logic gates. All right. So we have A and B, right? And now we have two possible states for each. So there are four possible inputs, right? So 0, 0, 0, 1, 1, 0, 1, 1. These are the four possible inputs. And we usually write this in this numerical order, which is because 0, 0 is the number 0, 0, 1 is the number 1, 1, 0 is the number 2, 1, 1 is the number 3. So we write them as 0, 1, 2, 3, the binary string in the binary strings. And then we have four possible outputs, right? Right? For each of those things. So since each of the four outputs can be 0 or 1, so there are two possibilities here, two possibilities here, two possibilities here, two possibilities. So there are how many gates? 16, yes. Very good. So there are 2 to the 4 or 16 possible 2-bit gates. Okay, so the first gate that we introduced is called the AND gate. And I already alluded to it in the beginning. So it's A times B, A and B, give me the output AB. Okay. Now what is AB? Well, AB is such, it's like multiplication. Like if you multiply two binary digits together, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and then 1 times 1 is 1. Okay. So, the AB, this output is true only when A and B are both true. So this is the logical statement. Okay. The output is true only when both A and B are true. And sometimes when I refer to actual digital circuits, I'll say the output is high when both the inputs are high. That's what a logical circuit is often. Well, you'll also hear high instead of 2 or 0 instead of 1. Instead of 1 you'll hear high, and instead of 0 you'll hear low. So, okay. Then we have the OR gate. Now OR almost looks like addition of the gates, and here's the gate symbol, right? It's this curved sort of gate, curved triangle, I guess. And then this is A plus B is the output. But it almost looks like addition of the binary digits, right? Because it's 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. But then 1 plus 1, if you added them with regular binary arithmetic, you get the number 1, 0. And if you took the last bit, you get a 0 here, right? So this isn't quite addition of binary numbers. Okay. So, but we can just say that A plus B or A or B, as you'll hear, and there's another symbol that you'll sometimes see in textbooks, which looks like, I should have written this over here. Let me see if I can sketch it. So A or B. So that's a symbol for OR, and will sometimes be represented as A. Sorry, it's really hard to. I should have brought a mouse. A and B will have that little inverted 2 lines. So, but that you don't need to know this. I was just going to say, if you ever read any other textbooks that have digital logic in them, you will see that addition. So then we introduce the gate that most looks, and the logic, the binary logic of this, or the Boolean logic, right? If you want to write this as a logical statement, is A plus B is true when either A or B or both, sorry, not are both, are both true. Okay. The XOR gate, okay, this is another one. So this is the addition of the bits A and B modulo 2, which is exactly what we were talking about earlier. So we take, what is modulo 2 addition? Is we take the remainder after dividing by 2. So in modulo 2, maybe I should just write this on the board. That's to be a little easier. Step. Oh. Wrong button. Sorry. We'll just have to restart this. Okay, so it's worth just a second to understand this, which is modulo 2 addition, which is that if I take 0 plus 1, right, that is 1, and then modulo 2 means I divide by 2 and I take the remainder. So when I divide 1 by 2, I get a quotient 0 and a remainder 1, so this is still 1. Okay. And of course, 1 plus 0 is the same way. It gives me 1, and then modulo 2 addition gives me 1. So 1 plus 0. One, 1, 2. Also equal to 1. 0 plus 0 is obviously 0. Then 1 plus 1 is of course 2 modulo 2. And that gives me a remainder again of 0. So in this truth table, then that's why 0, 0 with the XOR gate, which is given the notation A plus B with this circle. The circle denotes the modulo 2 addition and also denotes in this case the XOR gate operation. So this is A, this is B, and then we get 0, 1, 0, 0, 1, it's 1, 1, 0, it's 0, 1, and then 1, 1 is 0. So that is the XOR gate or the modulo 2 addition operator. Probably won't work. It hits it when I connect it with my laptop. Wait. Awesome. Okay. So that was the XOR gate. We already discussed the arithmetic and why it's modulo 2 addition. And now the logical statement is that it is true or high when either A or B are both true, but not both. That is, we can't have both of them being true, which is obvious from that truth table. Okay, the NAND gate is another important logic gate, and I'll explain why in a minute when we talk about gate sets. But it stands for the NOT of the AND gate. Okay, so you take the AND gate and you apply a NOT operation to it, and so it outputs a NOT of the AND of the bits A and B. And the logical statement is it is true when either A or B or both are false. Okay, so when they're false, when any one of them is false, effectively, okay, then you get a high. And if they're both high, then you get 0. The NOR gate is the output, is the NOT of the OR of the bits A and B will be true when both A and B are false and 0 otherwise. And you can make your own gate. Okay, you can cook up any kind of operation you want. Here I take A, I NOT it first, B, not that, and I get R of the two, which is A bar plus B bar. So why don't we work out now what the truth table for this gate should be, and you tell me what the truth table should be. I'll give you a couple minutes. Yes, you actually have to write something down. Get us started with A and B. And I won't write the A bar plus B bar, I'll just call it C. This whole thing is C. Anybody want to fill me in on the first row? Yes. One. One. Second row? Yes. One as well. Third row. Anybody? Yes. One. One. Fourth row? Yes.
You're right.
0. Everybody agree with this? See how easy it is to make your own gate? So is this equivalent to any of the gates we've seen so far? Yes, you. NAND. Very good. Excellent. Thank you. Awesome. So, sorry, before I move on. So of course there were 16 gates that I told you about, right? I said there were 16 possible gates that one can make from these, but I've only shown you like 4 or 5. And you may say, well, okay, so why don't we talk about all the 16? And and we'll come to that question in a minute. But before we do that, you'll see that it's actually very simple to construct your own gate. You don't need a complicated logic circuit to do it. You can do it with light bulbs and switches. Okay. So here is a simple 2-bit logic gate. We'll go through this in some detail, just so you understand what I'm talking about. Right. So the idea of this circuit hopefully is clear. There's a battery. It's connected in series. Okay, if you don't know what that word means, it just means the 2 switches are wired up like this. Okay, this fashion. And then it's connected to a bulb. Okay, and we say that the bulb being bright on is the output is 1, okay, binary 1, and the bulb being off is binary 0, right? So you can see when both the switches are 1, and of course the switches are 1 when they are on, and off means 0, right? So that's all you need to create a binary logic gate. So the inputs being 1, A and B being 1, this switch, both switches are on. The current from the battery can go through the switches, go through the wires, through the battery, and come back to the through the bulb and come back to the battery. And so it lights up. So that's output 1 for inputs A and B being 1. What happens if switch B is off? Output for the bulb? 0. Thank you. Similarly, if A is off, output for the battery? Yeah. For the bulb, sorry, 0. Yes. And finally, both are off, clearly 0. So the output of this circuit, what is it? What would I describe it using the language that we just discussed? It is only high when both A and B are high. Yes.
And, right?
And, exactly. Very good. So this is our working construction of an AND gate. And really, that's what is in an actual AND gate. Except instead of mechanical switches, we have transistor switches, CMOS FET switches. What about this gate? What gate is this? Constant gate? Yes, over there.
Inverter
It's an inverter. What is that?
on. It's the path of least resistance, the electric field of that happening.
Exactly. So it's a what gate? Not gate. Yes, exactly. Very good. Everybody see that? Right. It's a not gate. Okay. And okay, I'll leave this as a, well, let's see. We have 5 minutes. We could work through this. All right, let's work through it. Both switches off. The battery will drive the current all through this bulb, right? It'll ignore this path of the of this branch of the circuit, and therefore you'll get output high, right? Output is high. Similarly, if any one of the switches is on, it doesn't matter. The overall this branch is still off. There's no current through it, so the output will be high. So it's high when either A or B are zero or both are zero. Okay. And then it's low when both are switched on, because when both are switched on, that is when both are one, the current will flow entirely through the path of least resistance, which is those two switches, and therefore there will be no output voltage across the battery, across the bulb. Sorry, keeps saying battery there. So what gate is that? It's zero. It's one when either A or B or both are zero, and it's zero when both are high. Yes.
It's an AND gate.
NAND gate. Very good. Excellent. So that's it. Now you know how to make your own logic gates. Simple parts. Any questions on this? I have a couple more minutes. I guess I might as well talk about this since we have a few minutes to get through this part. So we can also add, I guess, sorry, the title of that should be addition of bits, but it came out as half added. All right, when we add two bits A and B, then we get the result, of course, as the sum, but we also need the carry bit. Remember, because we have the one situation where if you add 1 and 1, you get the sum as 1 0. So that is written here as the sum bit. The sum bit represents that lowest bit in that addition, and then the carry bit keeps track of the carry if there's a carry bit in the sum. Okay, so that's very clear here. I hope, right? 0 0 gives me a sum 0 and a carry 0. 0 1 is 1, and then carry 0. 1 0 is 1 0, and 1 1 is 0 1. Okay, so it's quite straightforward now to verify for yourself that S is just A XOR B. Okay, because as you can see, it goes to 0 when both are high, and is 1 when either one of them is high. Okay, so that is the XOR of A and B, and C, the carry bit, is just A ANDed with B. Okay, so that immediately tells us the construction of the circuit, right? Your half adder, as we call it, is just this circuit. We take A and B, we XOR the A and B, that gives me the sum bit, and then we AND the two signals, that gives me the carry bit. Okay, so this is the half adder. That's because we haven't quite completed the circuit. If we had one more bit in there, we would really want to do that. That's called the full adder, but I won't get into that today. Okay. The point is, along with this half adder, you can see that we can make up any set of gates that we want with a few of these simple gates, like the gates that we have discussed so far, not, and, or, etc. Okay, and Shannon showed that any function that takes binary strings and converts them to other binary strings, which is what a computational operation does, right? It takes a bunch of input binary strings, does some processing, and outputs another bunch of binary strings, right? And that and what he showed was any such operation can be efficiently written as a combination of a few sets of binary logic gates. Okay. So that is, these are called the universal gate sets. Okay. And examples of such universal gate sets are well known by now. For example, they are AND, OR, and NOT. Okay, that's one universal logic gate set. So what I'm claiming is any set of operations that I can carry out on, say, 16-bit numbers, right? I take 16-bit binary number and I want to convert it through some, you define some logical operation. You say, I want this output for this, or you create a truth table, basically, right? You say, if I have this set of 16 bits, I want this output. If I have this set of 16 bits, I want another output, etc., etc. You can create your own truth table. And there are powerful theorems in Boolean logic, which again, I don't have time to go into, and it's not really the focus of this class, so I won't bore you with that. You can do it, right? We have done it for the last 50 years, so you can take it for soon. And there are actually also nice computer programs that help you to do this. Maybe we'll go back to that sometime later on in the class so that you don't have to do this by hand. But the idea is that we can take any such truth table. Given a truth table, I can construct a logic circuit for that truth table. Okay, any truth table you want. There's a powerful things called Carnot maps and Boolean algebra, formulations that can help you to simplify any truth table to just a bunch of like 2-bit gates or maybe 3-bit gates at most. Okay, and so with those, and 3-bit gates can then be simplified to even further to 2-bit gates, basically. So in the end, we can all be written as combinations of 2-bit gates. So, or 2-bit and 1-bit gate in this example, right? So, and or not, that's two 2-bit gates and one 1-bit gate. Or then you can show that this and not can be made into an OR, okay? Which is pretty simple to understand. So therefore, just not an and is enough. Wait a minute, not an and is just so just one is needed, right? So that is the powerful simplification. Same thing with not and or. You can make not and or into and then of course not of and gives me NAND, therefore NOR must also be equivalent to NAND, right? Therefore, with just one gate, either a NAND gate or an OR gate, you can make all the possible logical operations. This is a powerful theorem, very powerful, right? When you think about it. Yeah. Okay, so that will bring me to the conclusion for today's lecture. I didn't think I'd get to this last little part, so that just is a summary for today's lecture. We've introduced classical digital computing and said that that's why the reason we want classical digital computing is that it's robust against errors. We've introduced binary arithmetic and logic, binary logic gates, and universal logic gate sets. Thanks. See you next time.